Hello once again, class, and welcome to another mock lecture. In this video, we're going to be tackling the limit laws. And here they are. These laws can be proved, shout out to the epsilon delta definition of a limit, but in this video, we're going to focus instead on just using them. So just to kind of talk about these a little bit, you have a basic law, the limit as x approaches a of a constant number is just that constant number since x doesn't affect it at all. There's nothing to plug x into here, right? It's just a constant. You have the limit as x approaches a of x being allowed to it's just approaching a, right? Those are our two basic laws. You've got these sum and difference laws, which are it's almost like a distribution, but you're just applying the limit as x approaches a to both functions that are either being added or subtracted. You have a constant multiple law, which says that if you have the limit as x approaches a of some constant times some function, again, x is not affecting this constant at all, so you're allowed to just bring it out. So you're multiplying just the limit as x approaches a of f of x by that constant. There's a product law and a quotient law, which say the same thing really as the sum and difference. It's just allowing us to apply the limit as x approaches a to both of these functions. You just have to be a little bit careful with the quotient law because you can't have the limit as x approaches a of g of x be equal to 0. Otherwise, you'd get something that's undefined. So let's do an example. All right, so example number 1. We're asked to find the limit as x approaches 1 of 2 times L of x times k of x. So using the limit laws, the first thing we're going to do is use the constant multiple law, which says that if you have a constant that's being multiplied by some function, you're able to just take it out of there. The next thing we're going to do is we're going to apply the product law. So we can essentially distribute, that's not really what's happening. We're more like applying the limit as x approaches 1 to both L of x and k of x. So we go ahead and do that. We apply the limit as x approaches 1 to L of x and k of x, and we get this. And then we just have to find, well, what are these limits? What is the limit as x approaches 1 of L of x? And what is the limit as x approaches 1 of k of x? Well, we have a graph, so we can just kind of look at that. It appears that as x gets close to 1, both from the left and from the right, L of x seems to be approaching the number 3. And for k of x, we appear to be approaching the number -2. So we get -12. Here's 2 more. And I invite you to pause the video and give these a shot. But I'm just going to go through them. The first one, the limit as x approaches -2 of L of x plus 7 times k of x. First thing we're going to do is use the sum law to break it up. And I'm also using the constant multiple law to kind of bring the 7 out in front of that second limit. The limit as x approaches -2 of L of x, if you look at the graph, even though there's a removable discontinuity at -2, right? Limits don't care about what's happening at the point we're approaching. It's just, does the left side agree with the right side? As x gets closer to the x value in question, do the y values agree? And in this case, the answer is yes. It appears they're both approaching 2. And for the limit as x approaches -2 for k of x, right, same sort of thing. They're both, in fact, this is just a nice line. There's not even a removable discontinuity. Not like that actually matters for limits, but the point is, here we get -2. Okay, so 2 plus 7 times -2 is 2 plus -14, and that's how we got -12 here. The second one is just a simple application of the difference law. So what I did is I applied the limit as x approaches 0 to both k of x and L of x individually, but right away we run into a problem because the limit as x approaches 0 does not exist for k. As you approach 0 from the left, it looks like your y values for k of x are approaching -3, and as you approach 0, as x approaches 0 from the right, it looks like our y values are approaching 0, and since those don't agree, we know the limit does not exist, which means that this limit does not exist. All right, now from these 6 basic laws, well, not this basic law, but from these 6 laws, we can derive 4 more that are super helpful. The first is the power law. And so still, by the way, I should mention in all of these, we're supposing that c is a constant, and also we're supposing that the limit as x approaches a of f of x and the limit as x approaches a of g of x exist. And it's really because of this that last one we just looked at did not exist, because this was not true. Right, or the other one. As long as they both have to exist for the limit of the combination function to exist as well. Anyway, the power law is really just an application of the product law. So it says that the limit as x approaches a of f of x raised to the n is the same as raising the limit as x approaches a of f of x to the nth power. And the idea for how we would go about proving that, right? This is more just kind of like, here's kind of the blueprint that we would use. This is more of an example. If I wanted to show that the limit as x approaches a of f of x squared is equal to this, well, the first thing that I would do is I would apply the definition of squaring to f of x squared, right? It means f of x times f of x, and because I have two functions here, I can then use the product law, applying the limit as x approaches a to both of them. But when you multiply something by itself, that's the definition of squaring, and so really by just the definition of squaring in the product law, we're able to show that the limit as x approaches a of f of x squared is the same as the limit as x approaches a of f of x quantity squared. The power law also gives us the x to the n law. It says that the limit as x approaches a of x to the n is equal to a to the n. And the idea for proving this one is if we just let f of x be equal to x, and then invoke the power law, there's just a small application of the basic law that said the limit as x approaches a of x is just equal to a. From the power law and also the x to the n law, we can generate the root law, which says that the limit as x approaches a of the nth root of f of x is the same as the nth root of the limit as x approaches a of f of x. Now we do have to be careful with these two laws because if n, right, if this thing is an even number, then this limit has to be something that's bigger than or equal to 0. Otherwise, you can't take the square root of a negative number or the fourth root of a negative number, so on and so forth. So this would only apply if n is an even number, assuming this is true. From the root law, we can also get the nth root of x law, which just like the x to the n law tells us that the limit as x approaches a of the nth root of x can just be simplified to the nth root of a. And by the way, the reason that we get these almost for free from the ones above it is because a root, like the nth root, is a power. It's 1 over n. It's raising something to the 1 over n. So it's basically still falls under the realm of power law and x to the n law. Similarly, that one just kind of produces this one because x to the 1 over n is what this is, and that's a power, right? So x to the n law kind of still applies. All right, so let's look at another example. All right, example number 2. We're going to use limit laws to find the limit as x approaches negative 3 of 2x squared minus 2x plus 5 over 1 minus 4x. All right, whole lot of stuff happening here, but let's break it down. First, we're going to use the quotient law. And we're going to apply the limit as x approaches negative 3 to the numerator polynomial and also the denominator polynomial. Then, in each part, right, of this rational function, we're going to apply the limit as x approaches negative 3 to each piece of the polynomial in its respective position of the fraction. So this limit as x approaches negative 3 was applied to the 2x squared, the minus 2x, and the 5. And in the denominator, the limit as x approaches 3 was applied to the 1 and the negative 4x. And that's just by using sum and difference laws. Okay, from here, we could use some constant multiple laws and some basic laws. The basic laws are happening here. There's a basic law that says the limit as x approaches a of some constant is just equal to that constant because x is not affecting it at all. So this limit just became 5, this limit just became 1, and then I used the constant multiple law to bring out this 2 here, this 2 here, and this 4 here. At this point, there's some more basic laws that are going to be at play, namely that this piece and this piece just get to become negative 3, and then this piece gets to be negative 3 squared, and that's an x to the n law. So we get 18 plus 6 plus 5 divided by 1 plus 12, which is the same as 29/13, and we are done. Now you might be looking at this, and you might be thinking, well, Mark, how is this any different than just taking negative 3 and plugging it into the function? You're exactly right, actually. That's called direct substitution, and that is the last limit law that we're going to talk about in this video. It says that if f of x is an expression built from basic pre-calc and trig functions, like in the last one, which was a rational function, and a is in the domain of the function that we're looking at. If we go back, a is in the domain of this. Right? Negative 3 is in the domain. It does not produce 0 in the denominator, and that's all you need to be in the domain of a rational function. Then the limit as x approaches a of f of x is the same as just f evaluated at that thing you're approaching, f of a. Here's a super quick example. First, we need to check that 0's in the domain of this rational function. So if I plug in 0 to the denominator, do I get 0? No. So we know that it's in the domain, right? In fact, the domain of this thing is everything except for plus or minus the square root of 2. And I got that by just setting this equal to 0 and then solving that equation. So we can just directly plug in 0 via the direct substitution law, and we get 10 divided by -2, or the limit as x approaches 0 of this rational function is just equal to -5. Now, when you're evaluating some limits, you always should try to use direct substitution first. Sometimes it fails, right? I mean, the first thing that you should check is the thing you're approaching even in the domain of the function you're taking the limit as x approaches whatever that value is. But always try to do direct substitution first. There are still times that it doesn't work, and so I wanted to go over some strategies you could use if direct substitution does not work out for you. So here's a few more examples. All right, example 3. The limit as x approaches -4 of 2x plus 8 divided by x squared plus x minus 12. First thing I'm going to do is figure out what the domain of this function is, because it's possible that -4 is not in the domain of this rational function. And by factoring the denominator into x plus 4 and x minus 3, we can very clearly see -4 is in fact not in the domain of this function. So what can we do? In this case, notice that there's a factor in the numerator that's exactly the same as a factor in the denominator. So the strategy here is going to be, once we factor, let's cancel some common factors. The limit as x approaches -4 of 2x plus 8 divided by x squared plus x minus 12 is the same as the limit as x approaches -4 of 2 divided by x minus 3. These graphs are actually the same. This one just has a hole in its graph when x is -4. But that doesn't, remember, for the limits, we don't care about what's happening at -4, we just care about what's happening as we approach it from the left and as we approach it from the right. Now we can use direct substitution. Plug in -4. If you plug in -4, you get 2 over -4 minus 3, which is -2/7. Okay, here's another one. Similar problem, right? You factor the denominator. 2 is not in the domain, right, of this function. But here we have a new problem. There is no common factor in the top that we could use to cancel out that problematic factor in the denominator. So what can we do? Well, there is still something that cancels, so we can at least simplify our rational function to just being 3 divided by x minus 2, and to figure out what the limit might be in this case. So the strategy that we're going to use for this one is using a sign analysis. So what I did is I plotted one of the critical points for this rational function. There's no x-intercept for this thing because there's nothing that makes the numerator 0. We can't get 0 for a y value. But there is a vertical asymptote, right? The vertical asymptote exists at x is equal to 2. And that's actually the only thing that could potentially change the sign of this graph. So what I was looking for was that if both sides are positive infinity or both sides are negative infinity, then we might have gotten something that did something like this. Right, or we might have gotten something that did something like this. That actually does not happen though, right? On the left of this vertical asymptote, the graph is always negative. And I know that because if you just plug in anything to the left of this vertical asymptote, like 0, this would be negative, and a positive divided by a negative gives us a negative on the left. On the right, plug in anything bigger than 2, like 3, that would give you something positive in the denominator, and a positive divided by a positive is a positive still. So the graph looks probably something like this, which means as you approach 2 from the left and from the right, our one-sided limits don't agree. One of them's positive infinity, that's the one as you approach from the right. One of them's negative infinity, that's the one that you approach from the left. Now to be super clear though, like no matter what, even if this side agreed, the limit here as x approaches 2 still doesn't exist, right? But we would say that it's equal to negative infinity so that we're informing the reader something about the behavior of the graph as we approach 2. But here, right, because one side's going to positive infinity and one side's going to negative infinity, we would just conclude that this thing does not exist. And if you wanted to find what the behavior was on either side of this vertical asymptote, then you just have to assess what the one-sided limits are. What about this one? We've got the limit as x approaches 7 of a square root of x plus 2 and then minus 3 in the numerator, and then the linear function x minus 7 in the denominator. Well, you can't plug in 7 because it makes the denominator 0, so we can change the way that this thing looks and hope that we can plug in 7 after we do some, what I'm going to call unsimplification. I'm going to rationalize the numerator, which is pretty weird. Typically, you want to rationalize the denominator, but rationalizing the numerator can help us use direct substitution. Remember, to rationalize something, you have to multiply it by its square root conjugate. So instead of square root of x plus 2 minus 3, I'm going to multiply both sides by the square root of 2 plus 3. Doing some box method stuff, or maybe you want to FOIL. Right, you'd have to FOIL like that. Your numerator ends up becoming x plus 2 minus 9, and your denominator is just this times this. Right, I left it like that. And I left it like that on purpose because the numerator actually simplifies to x minus 7, so that's pretty nice. Those are just gone. So we turned this thing into something that looks different. It's not a rationalized denominator, but crucially, you can use direct substitution on this thing. Right? You can plug in 7. So the limit as x approaches 7 of 1 over the square root of x plus 2 plus 3. 7's in the domain of this thing, so we can plug it in. So I did, and I got 1 over the square root of 7 plus 2, which is 9. The square root of 9 is 3, so the denominator is just 3 plus 3. Oh, and by the way, I'm just showing you that here we're using some quotient limit law stuff. But in any case, still direct substitution. I got 1 over 6. What about this one? The limit as h approaches 0 of 3 plus h quantity squared minus 9 over h. Again, you notice 0 is not in the domain, but in this one, if I just expand some stuff, which is what I'm going to do, then I would get, and by expand, by the way, I mean multiply this out. Right? That just gives you this. 9 plus 6h plus h squared. There's a plus 9 and a minus 9, so those cancel. And then what we're left with is just things with an h in it, so I can simplify everything by a factor of h to just get 6 plus h, and if you plug in 0, you just get 6. So in really all of these, well, I guess maybe 2 is not really categorized as an algebra that we're doing, but although to get to the sign analysis, we did simplify it. All of these things, I just kind of did stuff to the problem that we're allowed to do, right? I multiplied by conjugate, but I did the same to the numerator and the denominator. So it's like I'm just multiplying by the number 1. Rationalizing, right? That's the multiplying by the conjugate. Factoring and canceling, that's really just simplification. Expanding, right? That's just doing something to change the way the problem looks so that we can hopefully end up with something that you're allowed to use direct substitution on. All right, example number 6. Suppose we have a piecewise function. 3 does not appear to be in the domain of the piecewise function overall. So more importantly, if we were going to use direct substitution, what would we even plug it into, right? There's kind of 2 that are defined at the boundaries of 3. Because again, limits don't care about what's happening at 3 in this case. It's just what's happening as you approach from the left and as you approach from the right. Do those things agree? If the answer is yes, then the limit exists. So let's do that. Let's use one-sided limits for this piecewise function. We're going to start off by looking at what's happening as we approach 3 from the left, which is this part of the function, right? We're approaching 3 from the left. That's when x is less than 3. Oh, I just noticed I changed this sign. I mean, it doesn't matter anyway. We still need to know what's happening on the right-hand side. Anyway, the limit as x approaches 3 from the left of f of x, we're using this function here. So I just plugged in 3. I just used direct substitution on this part. And as we're approaching 3 from the left, we're going to get 4. The left-hand limit is approaching 4. From the right, we're going to get this. We're using this equation now, right? Because we're coming from the right. So that's all the values of x that are bigger than 3, but still getting closer to 3 on the x-axis. So we're going to be using this function rule. So here we replace f of x with the square root of x plus 13. I don't know why there's a negative here. Pretend that's not there because it's certainly just 3. And we plug that into x, which will be 16 underneath that radical. And the square root of 16 will be 4. So the left-hand limit and the right-hand limit agree. So then we can just conclude that the limit in general, right, this limit is equal to 4. Okay, so sometimes using one-sided limits, particularly with piecewise stuff, can be super helpful. Example number 7. Let's examine the limit as x approaches 0 of x squared times the sine of pi over x. There is not a whole lot we can do here, algebraically, to help us rewrite the way that this looks, right? Again, the problem here is you cannot plug 0 into this. 0 is not in the domain of this function. What you can do, though, is use this thing called the squeeze theorem. The squeeze theorem is this. It says that if you have a function g of x that can be bounded by a smaller function f of x and a bigger function h of x, for values of x that are near a, So this doesn't always have to be true for the entire life of the functions. It only has to be true for the values that are around a. And it says except possibly at a. So there could be like some removable discontinuity stuff going on here. And the limit as x approaches a of f of x and the limit as x approaches a of h of x both are the same thing. They both approach the same value. Then we can conclude that the limit of this function that's being bound by these two outer functions is also equal to L. And my picture is actually not technically correct, right? They should all actually kind of meet right at the same point, right? They should all be approaching the same y value right there. So in this example, it's just a fact that sine of theta is bound by -1 and +1 for all theta that are real numbers. I'm going to let my theta be pi over x, which means I can rewrite this thing. Right? This is true for all theta, so it's certainly true for this function. -1 less than or equal to sine of pi over x less than or equal to 1. It's just kind of by definition of the sine function and how it's generated by the unit circle. Anytime you multiply an inequality by a positive number, it preserves the inequality sign. The only time inequalities flip is when you're multiplying by a negative, but I'm going to multiply this whole thing by x squared, which is always positive. Even if x itself is negative, squaring it makes it positive, so it preserves those inequality signs, and multiplying all three of these pieces by x squared gives me this. Sine, oh, I forgot my x squared here, shoot. X squared times the sine of pi over x is bound by -x squared and positive x squared. So what I want to do, oh man, I forgot that x squared everywhere. That's okay. I'll put it in. I'll just put it in for right now. So what we have is the function -x squared and positive x squared. And by the way, I just graphed these things to see what we were dealing with here. This is the graph of x squared times sine of pi over x, right? Gives me this thing in the middle here. And just visually, it looks like maybe the limit of -x squared as x approaches 0 and x squared as x approaches 0 are the same thing. And in fact, they are. We can just use direct substitution to figure that out. This lower bound function's limit as x approaches 0 is 0, and this upper bound's function as x approaches 0 is also 0. So we can just directly invoke the squeeze theorem and say that, okay, so then the function that's bound between them, and just remember, I just miswrote this, just straight up forgot the x squared, but that function is supposed to be right here when you multiply everything by x squared, is equal to 0 by the squeeze theorem. Okay, so hopefully all that was helpful. I know that was kind of a lot of examples. If you have any questions, please shoot me an email or drop a comment below. Thanks a ton for watching, and I'll see you in the next one.